Can you take out your Chromebooks, open up Lab 3 so we can finish it up? I'm handing this out now because this will help you get started on the assignment that's due Thursday. But could you all get out your Chromebook, open up to Lab 3, the pendulum. We need to finish up the lab we started Friday. There isn't. So why don't you sit in the back row and you can pull down that yellow drop that's in the ceiling. Okay. So open up Lab 3, where we left off on Friday. This is your Unit 2 packet. Like I said, I'm just handing this out now so you can get started if you want on the assignment that's due Thursday. There are 2 videos posted in Google Classroom under classwork. It says Unit 2A videos. It's material. It's not listed as an assignment. So it says material. I'm just pushing out the video links for you to watch. They're each about 7 minutes. So it's a total of 14 minutes. And then as you watch those, I want you to complete the questions on pages 1 and 2. All right. It's kind of like a little bit about what we're going to be learning about if we finish this lab before the end of the period, which I suspect we will. My other classes all finished it in about 10 minutes, which gives us about 24 minutes to finish or to start working on Unit 2A, position, distance, and displacement, which is actually physics. Remember that tomorrow we are reviewing for your Unit 1 exam. So I definitely want to make sure I get you answers to the review assignment that you're doing for tomorrow. But you should also plan to bring other questions that you might have. Like, I really don't get this topic. Can you do some more of this? I don't understand this. What if I had something like this? What would I do? Bring those questions because that's your last opportunity to ask anything before we take our test on Wednesday. All right? Questions for me about any of that? All right, then let's go to the lab and let's just review where we left off on Friday. Took me a minute to think what day of the week we did this. We did this on Friday. So Anya, you're going to have to just catch up, okay, because I don't think you started it, right? Okay, so then you got to watch the videos. Okay, there's 2 of them. You got to get lab 2 and then get this one done at home. So just follow along and then you can finish this up at home. All right, so what we did on Friday was we did 3 experiments using the virtual simple pendulum simulation, PhET simulation that was linked to the assignment. We will be going back to that simulation to answer the last question in the lab. So in a minute, when we get there, I'll ask you to open it. But don't open it before that. It just takes up bandwidth for you and slows down your Chromebook. In the first experiment that we did, remember what we were doing was we were changing the mass that was at the bottom of the pendulum. We kept the angle of release at 9 degrees. We kept the length of the string 0.60 meters. And as we varied the mass, you measured, and then recorded the time for 10 of those swings, 10 outs and backs. The Google Sheet then calculated the period, the time for 1 swing, and it created data table 1, 2, which we then used to create the graph for experiment 1. And remember, in this experiment, we modified the graph to remove the units from the title. We made sure the graph started at an X value of 0. We added the trend line and the equation for the trend line. And I think we all saw that the graph was a horizontal line, pretty much horizontal. Then we did experiment 2, where we kept now the mass at the bottom of the string, 0.7 kilograms. We adjusted the angle. We changed that and we kept the length the same. Again, we measured 10 swings. The Google Sheet gave us the periods. And then we used table 2.2 to make a graph of the period versus the angle of release. And again, we adjusted this graph by deleting the units from the title, making sure our graph started at an X value of 0. We added the trend line and the equation for the trend line. And again, we should have seen that that graph produced pretty much a horizontal line for us if we have good data. Experiment 3, We kept the mass the same and the angle of release the same, but then we adjusted the length. We changed it from 1 meter all the way down to 0.20 meters. Again, measured the time for 10 swings. The Google Sheet calculated our periods for us. And then we used table 3.2 with the periods and the lengths to construct the graph for experiment 3. Again, we adjusted this graph to modify the title to delete the units. We made sure the graph started at an X value of 0. We added the trend line and we checked which was a better fit, linear or power series. And I think we all said power series was the better fit. And we knew that because all the data points were now pretty much on the curve, as opposed to with the linear, we had some of them that were off of it. So it is definitely a curve, the power series curve. And then we added the equation for that. And that's where we left off. Okay. Yes, that rings a bell. That's everything we did. All right. So let's now go to the analysis, which are our questions for today. I'm going to enlarge my screen so that way when I type stuff, you can see it better, although you should be able to answer most of these on your own anyway. So based on the data that we collected, which variable, and there were 3 of them, mass, angle of release, and length, affects the period of the pendulum the most? Which one affected it the most? Liam? Length. Now, how do you know? There's 2 ways you should be able to tell me you know based on what we did in experiment 3. How can I tell based on the data table? Yeah, it had the biggest range of periods. Okay, how can I tell when I look at the graph? How can I tell from the graph that the length is affecting the period? Should be an obvious answer. What were the other 2 graphs? What's this one? Not a horizontal line. Remember, if it's a horizontal line, what's the relationship? Starts with a C, ends with a T. Constant means things don't change. This is changing. It's the only one that shows that it's changing because we got a curve. All right, so let's go ahead and answer these questions with complete sentences. So the length, something like the length, you write it in your words. I'm writing it in mine. You do not have to copy what I'm writing. So the length of the pendulum affects the period the most. I know this because the data table shows the greatest variation in, or the greatest range of periods. And the graph is a curve. Something to that effect. Does that make sense? So not only are you telling me what the answer was, that it was length that affects the period, you're giving me the evidence that you have from the experiment, which clues you into that that's what's affecting it. How we know is because the data table has the greatest variation and the graph is a curve. Okay, let's now look at question 2. Based on your graph, what's the relationship between that variable and the period? So what is the relationship between the length and the period? So if you were to give me the name of this shape, let's do that first. What's the shape? I'm not asking you in the lab for the shape. I'm asking you in class. What is the shape of this? So if I were to extend the curve back, it would come back and intersect over here somewhere. So what's that shape? Starts with a P. Parabola. You got to just know that for Wednesday's test. And you should be able to spit it out like that. Shouldn't have to think about it. It's a curve that intersects an axis. It's a parabola. What is the relationship whenever you have a parabola? Quadratic. Good, Alucci. It's a quadratic relationship. So that is our answer for this. There is a quadratic relationship between period and length. All right, let's now go to question 3. This is where we have to do some additional work. Using our graphs, I want you to design a pendulum that should have a period of exactly 1.000 seconds. I want to know what mass should be at the bottom of the string, what angle you should be releasing it at, and what length the pendulum should have. Where do you think I'm going to get this information? Which experiment will help me figure that out? Yeah, let's go to experiment 3. Now, you're not going to look at the data table. You have to look at the graph. All of this data was collected with one mass and one angle. So we can assume that that's the mass and the angle that we're going to use. But the length we have to get from the graph, right? The lengths are down here. Here is that period of 1 second. What you need to do, and we can't do this the way our graphs are constructed right now. We have to make a change. Here is the 1 second period. You're all following me? Look up here. 1 second, we would read over and then down to get the exact length we need. The problem is, when Google Sheets constructed this graph for you, there weren't enough divisions between 0 and 0.25 meters, which means that you can't estimate this very much at all and have an accurate estimation. So what we have to do, like when we measure with a ruler, is we have to increase the small divisions between so we can get a more precise answer, which gives us a more accurate result. So let me show you how we modify the graph to do that. Okay, are you with me? That way we can more easily estimate what this length is right there, or whatever yours is, because you're going to read it from your graph, not mine. Okay, double click on your graph. And when you double click, you get this chart editor window. Okay. Notice, did yours open up this submenu grid lines and ticks for you right away? That's exactly where we have to go. Okay, this submenu. Now I want you to scroll down. Make sure it says that you're looking at the horizontal axis here first. Horizontal axis. You have an option between vertical and horizontal. We want the horizontal one, not vertical. You'll see that there are some check boxes. Major grid lines are the ones they're showing you. We want to add minor ones. And when you click minor, do you see you get some additional lines coming up? That's good. We have more subdivisions, but there's not enough. We're going to add even more. And I'm going to show you how to adjust to get that. When you look here, you see it says minor spacing type and minor count. You see where I'm looking? Right here? Okay. When you change the count, that will adjust how many grid lines we have between here and here. Because 0.25 is easily divisible by 5 or 10 or 25, those would be good numbers to pick. It's not easily divisible by 2. It's not easily divisible by 3. So what I would like to see, I think, for your highest precision is that we have 10 grid lines going from 0 to 0.25, which means we want 9 subdivisions in here, in that space, because this would be the 10th marker. So I want you to change your count to 9. I think it allows you to change it to 9, doesn't it? It does. Okay. Now when I count the grid lines, just like on a ruler, watch. You watching up top here on the screen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means each of these subdivisions is 0.025 meters. So you can get something much more precise now. You follow what I'm saying? All right. So this would be 0.25 minus 0.025. This one here would be 0.25 plus 0.025, and so on and so forth. You'll probably need your calculator to help you figure out what your length should be, because I doubt your curve crosses in the exact same spot that mine does. You may have to enlarge your graph. You can zoom in, right? And to then come down and get a good value. Go ahead and do that. I can see on mine that I'm about halfway between here and here. So I already know what that value is because I've been using this graph all day. So I've already done the interpolation. I know what my value is. Figure out what your value is. at a period of exactly 1 second. Read over and then down. Figure out what that is for you on your graph. If you need your calculator to help you figure out, okay, I have this many divisions. Each division is 0.025. Add or subtract from the 0.25, you can get your length. Okay. Once you have your length, you're then going to come over to question 3. And then we're going to type in the mass, the angle, and your length. Again, since we're using all the data from experiment 3, we're all going to be getting the same mass and angle because that was the mass and the angle that we used. So we're going to take those values, put them in here. It's 0.7 kilograms and 9 degrees. The length is based on your graph, not mine. When I do it, I get 0.2375, but I'm going to go ahead and type that in. And you'll see the Google Sheet rounds it. And the reason it's going to round it is because the simulation doesn't allow you to be more precise than that to the hundredths place. So type in whatever it is, the exact value. And Google Sheets will round it to what the simulation will allow you to input. Okay, once you've got that, you then have to open the simulation. Everybody needs to open that simulation back up. And go ahead and build that pendulum. Remember, you're going to get rid of the ruler and open up the stopwatch. You're going to adjust things. 0.7 and 9. Put in your length, whatever you figured out from your graph. Get it swinging. And then I'll tell you what you're going to do. You have to time now exactly 30 swings. Can you time 30 swings on your own? Okay. I'm going to do 30 of mine. You do 30 of yours. Oh, crap. I missed it. I got to start all over. That's all right. All right. I got my time. All right. Do you have your time? Okay. Now what you're going to do, go to your Google Sheet, and we're going to go to question 4. Question 4 wanted us to test the design. If that pendulum that you built had a period of exactly 1 second and we did everything perfect, how long should it take for 30 swings? Exactly 30 seconds. So notice we're setting this up for a percent error where the accepted value is 30.00 seconds. The measured value is what you just got right now. So we're going to go ahead and type in that as our measured value, whatever you just got, 29.53. And make sure you add a unit after it. Anytime we add a number, we have to, and we're typing it to do a calculation, we have to put in the units afterwards in our guess method. Now, what are we looking for? What's the unknown in this question? Percent error. So we're going to use our percent symbol and the word error. Okay, let me show you how you're going to type in this formula. Let me see if I can make this screen any bigger so it's easier for you to see. Yeah, that's probably better. Can you all see that better now? Okay, so start with, after the E, put in your percent error equals. Now, if you remember, when we do this calculation, we do an absolute value in the numerator. You need vertical lines. On my keyboard, it's above the enter key, above a backslash. To get it, because it's on the top of the key, I have to do a shift in that. Is it yours in about the same place? Okay, so shift in that key. Now I get my vertical line, so I can indicate I'm doing an absolute value. Then I'm going to do my parentheses, AV minus MV, close the parentheses, and then the absolute value symbol. So I'm going to take the absolute value in the numerator of this fraction. Then I'm going to divide by the accepted value. And then I have to multiply by 100%. That's how you get a percent error. Ring a bell? Okay. Now, what does that first S stand for? Substitution with units. So we're going to, whoops. That's wrong. Undo. Percent error equals absolute value, left parenthesis of the accepted value, which was 30.00 seconds, minus my measured value. You're going to use your measured value, 29.53 seconds for me. Then I put my absolute value, divided by my accepted value, 30.00 seconds, times 100%. Now you're going to go to your calculator, and you're going to work it out. And I'd like everyone to give me their percent error with two significant figures, okay? Please go ahead and work it out on your calculator. Do that calculation and round your calculator answer to two significant digits. Round it to two significant figures, please. Once you've got it calculated, you're done with the lab. Just make sure you move out of that cell where you typed your answer for the percent error. Hit enter afterwards. And then you can go back to Google Classroom and turn it in. And then you can put your Chromebook away. You don't need it anymore today. Can I close mine out, or do you need me to keep it up there because some of you are still working? Okay, I'll leave that up there for a minute. And then I'm going to ask you to take out the following things. So your clue to me that you're done is your Chromebook is away. Take care. So what you'll need for the rest of our class, once you've turned in that lab, you'll need your notebook, You'll need your pencil and a calculator. That's it. We're not going to get into the packet today. As I said, I just handed that out, so if you want to start the assignment due Thursday tonight, you can. Because I know many of you already finished the review. And that way you can kind of manage your time a little bit better. We're going to begin Unit 2 today, which is the real physics. Finally, we're going to get into physics. And we start kind of slow with some things that I'm pretty sure you learned in other classes, whether it was middle school science or whether you learned some of this in a math class, perhaps. But this is where we're going to begin physics, okay? Everybody all set for that? Okay. Unlike Unit 1, I don't have any PowerPoints for this unit. Because a lot of this is review of stuff you already know, I prefer to do this more as a conversation where we're just kind of writing things down to make sure we know what's going on. I do have last year's notes that I took with my students scanned in, and they're posted in Google Classroom. So if you're ever absent and you want to see what notes you missed, they're there, or you, of course, can watch the videos from each class. I think that's fair, but it's not a PowerPoint. You don't have to open up a PDF file like that to see what's what. It's a little more informal. But I think it's definitely more interactive. Okay, so let's get started with Unit 2. The title of Unit 2, be helpful if I unfroze my screen, yeah? There we go. The title of Unit 2 is Uniform Motion. Generally, what we mean by uniform motion is that your motion is constant. Basically, like you're traveling at a constant speed. What does it mean when you travel at a constant speed? But we're going to use a lot of different vocabulary things to describe what that means. So we're actually beginning an area of physics known as kinematics. Kinematics is the study of how things move. Not why they move, but how are they moving? We are describing how something moves. And kinematics is actually going to be in our course, units 2 through 5. So what that means is in each unit of study, we're going to be looking at a different type of motion. Different types of motion. This is all about uniform motion. So today, to begin our discussion of uniform motion, we have to introduce some vocabulary to you. The terms position, displacement, and distance. I'm sure you've heard of some of these things before. Maybe haven't defined them quite as precisely as we're going to in this class. Let's start with the first term, position. When we talk about a position, we're talking about where an object is located in an XY coordinate system. So let's define what we mean by an XY coordinate system. Let's do it through an example. This is an XY coordinate system. There's my positive X direction, my positive Y, my negative X, my negative Y. Let's say I have a particle located right there. And let's say that is at the 2-meter coordinate on the x-axis, and the y-coordinate is at 4 meters. It means that I would say the x-coordinate, which we're going to abbreviate as x, is positive 2 meters. We'll talk about what the positive sign means and why it's important. And then we have a y-coordinate, which we abbreviate with a lowercase y. We would say that is positive 4 meters. Now let's talk about what these positive signs mean. The positive or negative sign on a position tells you in what direction from the origin that particle is located. So because my x-coordinate is positive, it means that I am to the right of the origin. If I didn't put a positive sign, what you would just be telling me is that you were 2 meters away from the origin, but I would have no clue in which direction from the origin you were. Do you follow the difference? That tells me specifically I am to the right of the origin, which of course is right here. In the y direction, what do you think that positive sign means? I'm sure you know. What does a positive on a y coordinate tell you? Yeah, you're above the origin. Okay, so if I put a negative sign on that y coordinate, you would be telling me you were below the origin by 4 meters. So it's more precise, a more exact way to determine exactly where you are. Not just how far away you are, but in what direction from that origin. Because we include directions with these measurements, these types of measurements are called vector measurements. What do we have on a vector measurement? So all vector measurements include 2 things. Every time you have a vector, you're going to have to tell me 2 things. First, you have to tell me what's called its magnitude. Magnitude is a term that means size, or it could refer to an amount. Basically, how big or small something is. Think of when we hear about an earthquake, they'll tell you it's a magnitude 7 on the Richter scale, or a magnitude 2.5. The magnitude is telling you how big it is. Okay. And then the other thing every vector will include is a direction. So because these positions with x, y coordinates include a direction with respect to the origin and a distance away from the origin, they're classified as vectors. So position is a vector quantity. Okay, position's a vector. Now let's talk about how we can write directions. There are 3 different ways we can indicate direction on something. And let's draw an XY coordinate system to help us. I'll put it over here. So there are 3 ways you can specify the directions on something. The first way is with, how did I explain this to my other class? I want to make sure I'm staying consistent with how I'm explaining it to everybody. The first way we can state a direction is by using a word. We can say things like right, left, up, down, in, out, forward, backward, north, south, east, west, etc. Those are lots of different ways you could specify a direction by actually stating it as a word. On our XY coordinate system, well, that's where we're going to leave off. We'll pick up with more specifying directions tomorrow. All right, folks, have a great day. I'll see you tomorrow. Make sure your Unit 1 review is